actuary dude here looking at another exam question. So, an actuary has for 3 years recorded the volume of unsolicited advertising that he receives, and he believes that the number of items which he receives follows a Poisson distribution with a mean which varies according to which quarter of the year it is, and is recorded Yij, the number of items received in the ith quarter of the jth year, where I is 1, 2, 3, 4 quarters, and j is 1, 2, 3 years. The actuary wishes to estimate the number of items that he will receive in the first quarter of year 4, and has recorded the following data, being over here. So this is quarter 1 in year 1, quarter 1 in year 2, quarter 1 in year 3, this is quarter 4 in year 3. They've worked out already for us the averages for each of the quarters. So that's the average of all the 1 quarters, average of all the quarter 2 quarters, and so on. And over here, this is the sum of the standard errors. So this bit is 98 minus 113 squared plus 117 minus 113 squared plus 124 minus 113 squared gives us 362. And it's done that across all the quarters. So it says here, estimate Y1 for the number of items that the actuary expects to receive in the first quarter of year 4 using the assumptions of the empirical Bayes credibility theory model 1. Okay, so basically all with this question, you're just plugging numbers into a formula that they give you, and all that is over here. So we've got our unknown parameter, so we've got down that x bar, that's the mean of all the quarters over all the years, and then we've got all of these, which is just a lot of work to do to give us our credibility factor being z, which is the number of years plus, and I'll go into another video into the details of it, but this is basically, you know, the mean where they've already given us this is the sum of the squared errors that we've had, minus n minus 1, which is the number of years, minus 1, so we've had 3 years, so that'll be 2. You add all of that up, so all those sum of squared errors, that's been divided by 2, and then we're dividing that by the 4 quarters that we've got. And then for this bit, we're doing something kind of similar, just in a different approach. And I'll go into detail at another time. Anyway, I've put everything here on Excel. This is exactly what we just saw before. And so now, in order to find the first bit, well, let's first find that first bit here, which was the mean. So this bit over here, this 108, it's the average of these bits over here. So it's the averages of all the quarters over all the years. So any given quarter, we're expecting to get roughly 108 based on all this information that we've got. Is it the best predictor? Maybe, maybe not. Okay, so now to find out this bit over here, which we need. So to find that, I've already started, but basically it's the sum of the squared errors that they've already given us, but I'm just going to work it out anyway. So as I said, 98 minus 113 all squared. I'm going to drag that across to the right, pull it down as well, and then we're just taking the sum of these, but we're dividing it by, and it was divided by n minus 1, the number of years minus 1, which is 2. And then I'm dragging that down. So that's just this number here, divided by 2, divided by 2, divided by 2, divided by 2, added up gives us 109.75. That's a useful number that we've got there. And now we just need to find that third bit, and then we should be good to go. So the third bit says we do need this bit that we've already calculated, but now we're taking the averages of each quarter minus the averaging of all quarters over all years. We're squaring those, adding them together, and dividing it by the number of quarters minus 1, being 3 quarters. So I've just transposed this over here. It's just going across there. That's all fine. And we're taking 113 minus our mean of means, and we're squaring that, and in actual fact that's got to stay constant, and if I bring that one across, that gives us over here, I've worked out the sum of all of them divided by 3, which is 4 minus 1. And then I've already taken the liberty of working out what z is, but z is n number of years, 3 years, divided by the number of years plus this ratio over here, which is basically telling us how much we're to rely upon the quarters and how much to rely upon the other years. And it's saying here that we don't want, this number is fairly small, therefore that whole ratio is going to be fairly small, therefore z is going to be pretty big, saying that we should probably put a bit more reliance on the quarters. But now to then work out our final equation, we're saying that's going to be our z factor times the mean of risk I being quarter 1 plus 1 minus our credibility factor times, if we just assume that it didn't depend on quarters, it just depended, you know, in any quarter didn't make a difference. And that gives us 112.76. Okay, so I'll just write that. In fact, I don't need to write that anyway. I'll just make that nice and big. So that's the answer to part I. Now, the next bit, it says that the actuary believes that in fact, the volume of items has been increasing at a rate of 10% per annum. So suggest how the approach in I could be adjusted to produce a revised estimate taking this growth into account. Well, that sounds kind of similar to empirical Bayes credibility theory model 2, where you've got some risk factor affecting it. So basically what you could do is you could just adjust these numbers and you could try to bring it all to what year 4's figures would be. So if it has been going up by 10%, we can then, we can bring this one up, we can increase it by 10%, you know, for a few years, increase this one by 2 years, increase this one by a year. Or we could go the other way and bring it all to basically, well, kind of like present value, except we are in year 4, we bring it back to the first year's figures. So you can do it either way. So it's one or the other, doesn't make too much difference. Then for part 3, it says calculate the maximum likelihood estimate of that same thing we did, the first quarter, 4th year, based on quarter 1 data already observed and the 10% per annum increase described above, but we're using the maximum likelihood estimate. And normally that, you know, probably wouldn't affect the question too much, except luckily they did give us that, this follows a Poisson distribution. Okay, so, sorry, I keep jumping backwards and forwards. So let's try to figure that one out. Now, using the Poisson distribution and maximum likelihood, we're saying that that's analogous over there to e to the negative lambda, which we don't know what it is, lambda, and then that's going to be quarter 1, year 1. And we're just going to keep multiplying that by e to the lambda's now gone up by 10% times lambda 1.1, and that's to the power of, that's still quarter 1, year 2. And then we've got e again, negative lambda 1.1 squared, hopefully this will all fit, lambda 1.1 squared, y1, 3. Okay, looks a bit complicated, so we just take the log of that, and so the log being the ln of the likelihood, which is then negative lambda plus, we're plugging y11 ln lambda minus lambda 1.1 plus y1, 2 ln lambda 1.1. I'll just write it over here, continuing, minus lambda 1.1 squared plus y1, 3 ln lambda 1.1 squared. And then we have to basically take the derivative. We're going to be taking d of the log likelihood of d lambda. That's going to be equal to, but we can actually simplify this first, so let's just save this step for the next line. But basically here there's a lambda by itself, lambda and lambda, so we can take out negative lambda, and then we've got our 1 plus 1.1 plus 1.1 squared. And we can also fix up these ones. We can notice that there's a log lambda, so we can actually take out plus ln lambda and put in there y1 plus, we take out y1, 2, and in fact I'm skipping a step over here because what's really happening is this would just be, for example, this bit is ln lambda plus ln 1.1, and that bit I'm just going to save for later. So there we have y1, 3, and then we've got plus our ln 1.1 plus ln 1.1 squared. And then when we take the derivative of that, we're almost there. That's just going to be negative, whatever this is, that's 1.21, 2.31, 3.31, so negative 3.31, plus, and that's then going to be y1, 1 plus y1, 2 plus y1, 3, all over lambda, and that's going to be equal to 0. And then we'll be able to find out what lambda is equal to. It's then going to be this sum over here divided by 3.31. So whatever that whole thing is divided by 3.31, will give us lambda, which will then equal, well, we'll find out. So in order to find that one out, all we did was saying it's the sum of quarter 1 year 1, quarter 1 year 2, quarter 1 year 3, like that, divided by 3.31 gives us 102.42. Okay, so I'll just put that one maybe over here, and that's also an important one, so that's the answer to part triple I. And then lastly, question 4 says compare the assumptions underlying the approach in 1 and 2 with those underlying the approach in number 3. And well, really the difference is that all we did in all of this calculations here is we've only used quarter 1 for all the years. So we've actually ignored what quarter 2 can do for us, quarter 3 can do for us, and quarter 4 can do for us. So whichever one's better or more relied upon, this one's using at least 5% of this mean of all of these figures, whereas this one completely ignores and says we don't care about quarters 2, 3, and 4. We just want to know what we're looking at over here, and I guess that'll tell us. So as you can see, there is some difference there. Which one's going to be better? I don't know. You be the judge. But that's the answer to the question, and thanks for watching.